presented is Sir Gianandrea.
My name is Corrado Maggi, and I'm here on behalf of Politecnico of Milano because the professor and Vittorio Gianandrea Messa has been locked in Munich by a problem of transport at the airport that he could not join us. I'm a co-author of this paper, and so of course I will not be as prepared as the Professor Messa, which is Associate Professor for Fluid Dynamics in Politecnico of Milano and hydraulics. But I know the subject because the subject's been committed by our company, and I've been project leader for this.
Okay,
thanks.
No problem.
So, of course, Politecnico of Milano, he has a specific department for fluid dynamics, and Gianandrea Vittorio Messa. If anybody after this speech will need to be in contact with Professor Messa, I will be happy to share your data, your information. We will also have a webinar outside this because to try to solve this issue. What we are speaking today is about the validation of a computational fluid dynamics method for applications in filter bag. So in bag house, basically filter bags and cage, filter cage, is something that has already been studied, of course, but in the literature that we found, probably not so well on the base of modeling. So if we look to, let's say, the technology which is behind, we already find that, of course, we need to remove dust from bag filters, and for the ones who knows, but I believe everybody knows here, of course, the push jet for cleaning is generated by a nozzle, a specific nozzle that is causing a pressure wave traveling over the filter bags. Filter bags are very often long, so we concentrate our study on long filter bags. And wave shakes the filter bag by sporting the dust cake, partially the dust cake, and so renewing the efficiency of the filter when the pressure the delta pressure is too much for a good filtration operation. So, of course, we look at some literature. We found some studies. There was one Chinese study, especially by Yuan Chen in 2019, which was of interest to us because the efficiency of the shooting seems in some way tied to the frequency of the cleaning. And so we concentrate basically on two parameters. On beta and third one, but the two parameters were the peak pressure. High peak pressure seems to have a better cleaning impact, especially if we can lower the peak pressure arrival time at the end, the bottom of the cage. So you can see the two graphs on the right, the peak pressures and the arrival time. Of course, the peak pressures it generates and moves along with a peak wave along the filter bag. So when you face how to look to methods that can avoid some experimental methods is a question of money and time. So how we can rely on computational fluid dynamics if we want to apply these methods to vary parameters and gaining information in a quick manner, relatively quick and cheaper manner. So the fact is that we can have distributed information, but we have some advantages in computational fluid dynamics. We do not suffer from size constraints, for example, and as I said, it's less expensive. But on the other side, the computational burden, as soon as it's based on the difficult equations, and for this, Professor Messa would be of greater help. I mean, from perspective of my knowledge, introduces a source of uncertainty in the system. So you have to consider 4 or 5 equations, a lot of parameters. And so producing reliable computational fluid dynamics models is not so easy. And that's the study. These are the parameters, numerical factors, but also modeling factors that produce uncertainty in the system. So we have typical numerical factors like the computational mesh choice, but also time discretizations that should match the computational numerical settings, algorithm, post-processing, but also some typical physical parameters which are typical of the model that we are analyzing. I mean, filter package and pulse technology. So fabric filters, permeability, for example, so thermodynamic aspects tied to temperatures. These filters work at often also 250 degrees, for example, or fluid dynamic models to be chosen to represent the equations that solve the problem. So from physical consistency, that's the proposal work forward we follow up to analyze numerical convergence, particularly computational measured time steps, see them as coherent with some experimental data that we found, impact of modeling factors like turbulence model we said before, but also fabric filter model coefficients, and then experimental validations to the applications. That is was of course what was interesting the customer, the CleanAir company. So we represent, this is the way that has been made the study, is axisymmetric to the domains in order to simplify, and it has been used to model fluid dynamics compressible neurons with ideal gas, using Darcy's filtration model for what is concerned with fabric filter, and with a two-stage strategy. Of course, we concentrate to extend the tank, then we close the tank, and then the air is coming in traveling phase in what is on the right side in the blue part, the representations of the bag constraints, the bag limits. So, and of course, at the end there was bottom cap when in some cases been considered. So we started with 6 pressure with a qualitative assessment with a time pressure of 6 bar. Then we also made test at 2 bars. Of course, we have to choose some sets of parameters to look after our study. And then first we have looked to what is the main parameters we would like to analyze. So we analyze speed, we analyze pressure, we analyze peak pressure, and we analyze the arrival time of the peak pressure. Step 1. In step 2, we consider the fact that there are barriers in modeling and using computers, time limits, constraints, especially it's long time to, in case you use a time step size of 1.2 at 6 is 40 days work for a computer. So we have to face the problem to have check the variance deviation, standard deviation of the values, and compare them with a suitable working day, especially if we want to analyze several. So we find out that the time step of 1.5 appears a reasonable choice for the model, and then we analyze also the mesh. So also having a very wide mesh structures for the model, it takes also very long time. So we try to fix if we can use a good mesh that is representing in reality the value, and with sensitivity analysis. This has been done both for time and mesh. So this is represented on the right, the variation of the results in peak pressure and arrival time. So then we choose also the 50K cells. So the combination that we finally choose to make a computational fluid dynamics for representations of this model was based on delta T and E with 5, minus 5, and E to 5 and 50K cells. There are still some aspects that could introduce, of course, we can better the process, but the process will be time consuming otherwise and research cost consuming otherwise. So it is really necessary, not so necessary if we can consider that the error, the mistake that we are adding is not significant in the sense that we are not looking to absolute value. We will use computational fluid dynamics by comparative. So by comparison, we can say this solution is better than this. We don't say, this is absolutely better and the results we found is certain. That we cannot say, but we can say that the model is representing the physical behavior of the fluid dynamics aspects. So besides this numerical aspect, there are typical of, let's say, applications, typical aspects like a fluid dynamic model. This is, I'm really not an expert for this. Professor Messa is an expert. So like the compressible, incompressible, the Urans method, so they utilize the turbulence model and so on. And then thermodynamics, so the other equation, the anomalies are needed, as far as I understood, to solve the Navier-Stokes problems. No? We saw equation of state energy conservation equations. So other data are needed, and then typically the fabric filter model, so for example, permeability law, coefficients and so on. So we also tried to fix, at least to work on two of these. So by the effect of turbulence model, we made a sensitivity analysis on the two models that has been considered, and we see there was some variation, of course. Minor influence of permeability coefficient that was considered as 10 minus 7 instead of 10 minus 13. Why 10 minus 7, 10 minus? Because we have looked to the literature of experimental that has been done over the time that normally take these two kind of permeability as references. Of course, it has been defined a system where we have distance 10 meters. We have worked with 10 meters. A certain nozzle has been fixed, a certain distance in between the nozzle and the collar. And then we have started to study, of course, some, let's say, typical geometry. So that's what is said for the experiment. We have validated in some way the computational fluid dynamics by looking at this study of Liu and Chen of 2019, where we put into the model exactly the same figures, and we look at what was happening with those figures, if they were really representing a real value, close value to the value that have been experimentally obtained by sensor. And we found that the computational fluid dynamic system that we chose was working. So it was representative of the figures effectively got by this. So why doing all this? Because we would like to investigate some shapes of Venturi that could raise the peak pressure and decrease the peak pressure about time. So basically we start to design different layout, Venturi 1, Venturi 3. They are not represented here because then the result of this has been a patent also. So this is the job that has been done later. So what is the conclusions? What will be the next step? Of course, the aim for Politecnico of Milano was to demonstrate that the tool of modeling could be a good tool to be used, of course, with some burdens, but also with as a comparison tool to make a relatively fast investigation, because we can change in the model some geometry, some parameters, and get back in 1 week the answer by being enough sure that at least by comparison we can confrontate the different geometric designs of the cages. We are CleanAir is manufacturer of cages. And of course the scope was also explorative, first it has been done by looking at several documents made by experts in the field trying to find the common lines that are guiding. Frankly speaking, we did not find so many computational fluid dynamics work that have been so widely studied in the hypothesis forward hypothesis at the beginning. So, or maybe they have been, but their study has not been so clear expressed. Some parameters not clear expressed in the study itself. For example, the mesh time, discretizations of mesh and time. So basically, the conclusion of this job, which is job discontinuous in our research, is that the design optimization of a convolutory color could be done with this technique of computational fluid dynamics. And the finding, as I said before, goes into the concept that by increasing the peak pressure, decreasing the peak pressure arrival time, increasing the air inlet is all possible. We can have a better, let's say, a better filtration operation in the sense, the cleaning operation in the sense that we can reduce the frequency of the cleaning, and by reducing the frequency of the cleaning on average, bettering the delta pressure over the time and the compressor consumption, but also the fan energy need for the proper functionment of the Filtech systems. So, I believe that's all. Of course, to Gianandrea, Vittorio, Messa, the professor is him, you can see. He would have made, for sure, a better speech than me. And I am Corrado Maggi with Montanelli. We are the co-authors of these jobs, and we work for CleanAir, the company that committed to the Politecnico of Milano. Politecnico of Milano is the most important university in engineering of Italy. At least I am an engineer from Politecnico of Milano, so I'm a fan. But you can check, it's really like this. So thank you for your attention.
Thank you. Let's go to the discussion. One question? Nobody? It's very difficult to compare, to the simulate and the data, but in your paper, they simulated for 10 meters for length.
Yeah.
And when you compare with 4 meters with the data. Why?
Yeah, of course, long filter is nowadays most used in some, let's say, typical installation for where a big treatment of air inlet is needed, millions cubic meters per hour. And there, of course, we need a big dust collector. And big dust collector means a big surface of air filtrations along the cage. Of course, the nozzle is injecting air. We need to, let's say, work on the, for example, peak pressure parameters when we have longer cage, because this wave propagation takes 10 minutes to arrive. And that's the reality of the market, that we have a lot of 10 meters cage or 8 meters cage. And so we study to improve the dust cake or homogeneity along the 10 meters. So one of the effects of what we are doing is try to raise up the second part of the peak pressure curve in a way to have a more stable, of course decreasing, but layer deposit of layer of the dust cake along the cake, and not clean part and bad part, because this is affecting the efficiency of good cleaning, and just cleaning what is not to be clean, and this is caused by one bad part that needs to be cleaned instead, because it lowers the difference. It keeps the different pressure trigger. Okay. So the idea is this seems far away from eco-design, but this is really eco-design. That's what we are trying to do is eco-design. Save energy means also sustainable work, sustainable product. and less consumption. Energy is costing in carbon footprint, is costing in sustainability as well. So that's the aim for CleanAir. Of course, in Politecnico also I do well understood this principle.
Okay. More questions? Okay, thank you
Thank you
very
so much.
And congratulations, you're a great presenter.
Thanks.
Well, let's finish.